Have you ever wondered how long it would take to fall to the center of the Earth? Picture this. You're standing on the surface of our planet and suddenly a trapdoor opens beneath you. You're falling, plummeting into the abyss. But this isn't just any fall. This is a journey to the very heart of our world. Now, before we embark on this imaginary descent, there are a few things to consider. The Earth isn't a uniform sphere, it's a complex structure with different layers, each with its own unique characteristics. And then there's gravity, the invisible force that keeps us grounded. Its effects aren't constant as you dive deeper into the Earth. And here's the kicker. If you could survive the heat and pressure, and if there were a tunnel going straight through the Earth, this fall would take approximately 19 minutes. Intrigued? Now let's explore the physics that would govern this hypothetical 19-minute journey to the center of the Earth. Gravity, as you know, is the force that attracts two objects towards each other. It's this invisible tug-of-war that keeps us grounded, literally. It's why when you jump, you don't just keep going up into the sky, but instead you come back down. It's why planets orbit stars, and it's what keeps the stars themselves together. Now, gravity works according to certain laws. The most famous of these is perhaps Newton's law of universal gravitation. This law states that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Sounds complicated, right? But in simpler terms, this means that the more massive an object is, the stronger its gravitational pull. And the further away an object is, the weaker that pull becomes. Let's take Earth as an example. The Earth is quite massive, which is why it has a strong gravitational pull. This pull is what keeps us and everything else on the surface from floating away into space. But here's the thing, this gravitational pull isn't the same everywhere on Earth. It changes depending on where you are. At the Earth's surface, for instance, the gravitational pull is at its strongest. This is because you're as close as you can get to the Earth's mass without actually going inside it. But what if you could go inside? What if you could somehow tunnel your way to the center of the Earth? What would happen to the force of gravity then? Well, as you descend towards the center, the gravitational pull actually decreases. This is because as you go deeper, there's less and less of the Earth's mass below you to pull you down. And more of it is above you, pulling you up. In fact, if you were to reach the very center of the Earth, the force of gravity would be zero. That's right, zero. You would be pulled equally in all directions, and so you wouldn't feel any gravitational force at all. This reduction in gravity as you approach the Earth's center would affect your speed of fall. You see, the force of gravity is what accelerates objects towards the Earth. It's why, when you drop something, it doesn't just fall at a constant speed, but instead it speeds up as it falls. So if the force of gravity decreases, then this acceleration also decreases. In other words, as you fall towards the center of the Earth, you would start off falling quite fast, but then you would slow down. And when you reach the center, you would stop falling altogether. So as we get closer to the Earth's center, the force of gravity decreases, affecting our speed of fall. Our planet isn't a solid sphere, but a series of concentric layers. This is the fascinating structure of our Earth, which is divided into four main sections: the crust, mantle, outer core, and inner core. Let's start with the crust. This is the Earth's skin, the part we live on. It's the thinnest layer, around 25 miles thick on average. It's made up of light, solid rocks such as granite and basalt. If you were to start falling through the Earth from the surface, the crust would be your starting point. Next up is the mantle. This is the thickest layer of the Earth, making up about 84% of the Earth's volume. It's made up of denser, semi-molten rock. As you fall deeper into the Earth, the increasing density of the mantle would cause you to speed up. Now we're getting to the Earth's core, which is divided into two parts, the outer core and the inner core. The outer core is a band of extremely hot liquid metals, primarily iron and nickel. This layer is denser than the mantle, and as such, you'd continue to speed up as you fall through it. Finally, we reach the inner core. This is the densest part of the Earth, made up of solid iron and nickel. This layer is so dense that as you fall through it, you'd actually start to slow down due to the immense gravitational pull. So as you can see, the structure of the Earth isn't uniform. It's a complex layering of different materials, each with its own density. And it's these differences in density that would affect your speed if you were to fall through the Earth. Your speed would increase as you fall through the denser layers of the mantle and the outer core, but then it would decrease as you hit the super dense inner core. The varying densities of these layers play a significant role in our 19-minute journey to the Earth's center. Now, let's piece together our understanding of gravity and the Earth's structure to explain the 90-minute fall. Imagine dropping an object into a hole that goes straight through the Earth's core. What happens next is a complex dance between the gravitational pull and the density of the Earth. As the object falls, it's pulled towards the center by gravity. However, it's not a straight, constant pull. The force of gravity decreases as we move closer to the center because there's less of the Earth's mass pulling us in. At the same time, the density of the Earth is increasing. We start from the crust, which is relatively thin and not very dense. But as we move inwards, we hit the mantle and the outer and inner cores, where the density significantly increases. This increased density provides a counteracting force against gravity's pull. Now, here's the interesting part. The decrease in gravity and the increase in density balance each other out. This means that the speed at which the object is falling will not keep increasing indefinitely. Instead, it will reach a constant speed, also known as the terminal velocity. So how does this all add up to a 19-minute fall? Well, let's break it down. First, the object accelerates due to gravity, reaching high speeds as it plunges through the Earth's crust and upper mantle. But as it descends further, the gravitational pull weakens and the Earth's density increases. The object begins to decelerate, but it's still moving quite fast. When it reaches the Earth's center, the gravitational pull is now zero. There's no more down, only up. But the object's momentum carries it past the center and up into the other side of the Earth. Here, it begins to slow down as gravity pulls it back towards the center. This oscillating motion, speeding up, slowing down, speeding up, continues until the object finally comes to a rest at the Earth's center. And this whole journey, if uninterrupted by the Earth's intense heat and pressure, would take about 19 minutes. To put this into perspective, it's faster than a New York to Los Angeles flight, which typically takes about 5 hours. It's even faster than the International Space Station orbiting the Earth, which takes approximately 90 minutes. So, in theory, if you could withstand the immense pressure and heat, you would reach the Earth's center in about 19 minutes. Quite a journey, don't you think? But would this journey be a smooth one? Let's delve into the numerous challenges that would be encountered during this hypothetical fall to the center of the Earth. Right off the bat, we have to contend with the fact that the Earth isn't a hollow sphere. It's a solid mass filled with layers of rock, metal, and other materials, all of which would pose a significant barrier to any would-be traveler. Then there's the increasing pressure to consider. As we travel deeper into the Earth, the weight of the material above us would increase exponentially. This increasing pressure would be like having the weight of the world, quite literally, on your shoulders. And let's not forget about the rising temperature. The Earth's core is incredibly hot, reaching temperatures as high as those on the surface of the Sun. This extreme heat is due to the decay of radioactive materials, as well as residual heat from when the planet formed over 4 billion years ago. Even if we could somehow withstand the pressure, the intense heat would make survival impossible. Now, let's address the elephant in the room, the impossibility of a vacuum tunnel through the Earth. For our journey to be possible, we'd need a tunnel devoid of air resistance, which would require a vacuum. However, creating such a vacuum on Earth is virtually impossible. Firstly, we'd need to overcome the atmospheric pressure at the surface, which is the force exerted by the weight of the atmosphere. This pressure is strong enough to crush a vacuum-sealed can, let alone maintain a vacuum tunnel through the Earth. Secondly, even if we could somehow create a vacuum tunnel, it wouldn't remain a vacuum for long. The immense gravitational pull of the Earth would draw in air and other particles, quickly filling the vacuum. Moreover, we'd need to contend with the Earth's rotation. The Earth spins on its axis, causing anything on its surface to travel in a circular path. This rotation would cause our faller to slam into the side of the tunnel, rather than falling straight down. Lastly, there's the issue of the Earth's magnetic field. This field is created by the movement of molten iron within the Earth's outer core. While it's essential for protecting us from harmful solar radiation, it would wreak havoc on any electronic equipment we might bring with us on our journey. Clearly, this journey, while fascinating in theory, presents numerous insurmountable challenges. From the physical barriers to the increasing pressure and temperature, to the impossibility of creating a vacuum tunnel through the Earth, It's clear that our hypothetical journey to the center of the Earth remains just that, a fascinating thought experiment but far from a feasible reality. Despite these challenges, why do we even ponder over such a hypothetical scenario, you might ask? Well, it's not just for the thrill of a mental roller coaster ride. It goes much deeper than that, into the core of our understanding of the universe and the laws that govern it. Imagine for a moment the wealth of knowledge we could gather from this thought experiment. By considering this hypothetical fall to the Earth's center, we delve into the intricacies of gravitational forces. Gravity, that invisible force that keeps us grounded, is not just a one-way pull. It's a complex interaction between objects, and understanding how it would behave in our scenario helps us grasp these complexities. It sheds light on how gravitational forces change with distance, the distribution of mass, and how these forces might interact within a planet. Then there's the Earth's interior, a realm that remains largely unexplored due to its inaccessibility. Our journey to the center of the Earth, albeit hypothetical, provides a unique perspective to visualize and understand the different layers beneath our feet. It's like an imaginative trip through the Earth's crust, mantle, outer core, and finally the inner core, each with its unique properties and challenges. And let's not forget the science of free fall. This concept is not just about falling, it's about motion, speed, acceleration, and how these elements play out in different environments. Our 19-minute fall is a fascinating study of free fall in a non-uniform gravitational field, a concept that has implications in various fields like aeronautics, space travel, and even sports. So you see, this seemingly far-fetched scenario is not just a fanciful daydream. It's a thought experiment that pushes the boundaries of our understanding, encouraging us to question, explore, and learn. It's a testament to the power of theoretical physics, where even the most fantastical scenarios can offer valuable insights. In the realm of theoretical physics, even the most fantastical scenarios can offer valuable insights. So, what have we learned from our hypothetical fall to the Earth's center? Well, we've embarked on an imaginary journey that has taken us through the core concepts of gravity, the layers of the Earth, and the intriguing idea of a 19-minute fall. It's been a dive not just into the center of the Earth, but into the heart of physics. We started by understanding gravity. This omnipresent force is the invisible tether that binds us to the Earth. It's what keeps our feet on the ground, and it plays an integral part in our hypothetical fall. In our journey, gravity is the vehicle that propels us towards the Earth's center. Next, we explored the structure of the Earth. From the crust to the core, each layer presents unique characteristics and challenges. The Earth is not just a solid block, but a dynamic structure with a molten outer core and a solid inner core. This deep dive into the Earth's layers has offered us a unique perspective of our planet. Then came the calculation of the 19-minute fall. Using the principles of physics, we've discovered that if we could somehow drill a hole through the Earth and fall, it would take approximately 19 minutes to get to the other side. This calculation is not just a whimsical thought experiment, but a testament to the power of theoretical physics. Finally, we looked at the theoretical applications of this concept. While a physical journey to the Earth's center is currently impossible due to extreme temperatures and pressures, the thought experiment serves as a fascinating exploration of gravitational forces, Earth's structure, and theoretical physics. While we may never physically make this 19-minute journey, the fall to the Earth's center offers a compelling exploration of physics and our planet. It reminds us that sometimes the journey is just as important as the destination.